Okay, this is mechanics unit video 1. So I get that box to go away. Guess not. It's all right. So for this unit, we got quite a few learning goals. I want you to be able to use mechanical advantage to calculate torque. I want you to be able to use mechanical advantage to calculate linear speed. I want you to be able to calculate the traction of a wheel. I want you to be able to calculate the torque needed to move a lever arm. And finally, I want you to be able to calculate efficiency. So we're going to have to cover a lot of review material before we get to some of these learning goals. So let's review linear kinematics. This is a study of motion. We're going to primarily focus on 1D, but I'll also show you some 2D, some projectile motion. So there are two main types of motion: constant velocity and constant acceleration. So when we have constant velocity, the object will move without speeding up or slowing down. So a bowling ball is a great example of this, because once you get a bowling ball moving down the lane, it's not going to speed up because you're not adding anything to it, and it's not going to slow down because there's so little friction between it and the floor. So a bowling ball is actually a really good example of constant velocity. So if I were to make a position versus time graph for constant velocity, I would see a nice even change in the object's position with time. If I were to make a velocity versus time graph, I would notice that the velocity would be it would be a horizontal line because the velocity is not changing. Now, since the velocity is not changing, that means the acceleration will be 0 because it's not speeding up or slowing down. So for constant velocity, the acceleration will be 0, and one of the ways we have of calculating this is to take its final position minus its initial position divided by time. Now, for constant acceleration, this is where the object's velocity changes uniformly. So in this one, let's start with the velocity graph. So if the velocity is changing uniformly, I would see some sort of line, some sort of linear relationship. And then if something has a constant acceleration, then we should see a horizontal line on the acceleration graph. So now coming back to the position graph, well, if I think about this, since something is getting faster, initially it's moving slowly, so it's not covering very much ground. But as more time passes, it speeds up and covers more and more ground. And that causes this graph to curve up, kind of like a parabola. So for this one, instead of being 0, the acceleration will equal the final velocity minus the initial velocity with respect to time. Very similar to the constant velocity graph. We want to understand these differences between acceleration and velocity. So, for example, what is the acceleration of an object that's been thrown vertically into the air? Well, if we think about it, as soon as the object leaves your hand, it begins to slow down. So it does experience an acceleration. And as it slows down, it's going to move slower and slower and slower until it reaches 0. Turns out that that acceleration is negative 10 meters per second for every second it's in the air. So if I give something an initial velocity of 20 meters per second, so at t equals 0, it's moving at 20 meters per second. After 1 second, it's moving 10 meters per second. After 2 seconds, it's moving at 0 meters per second. That's at the very top. And then it begins falling again. What is the acceleration of the object at its highest point? Many people will say 0 because they say the object, hey, it stopped moving. It's not moving, so it must have 0 acceleration. But remember the definition of acceleration. It's a changing velocity. So if the acceleration were 0 at its highest point, the velocity would not be able to change, and it would not be able to begin falling again. So, believe it or not, at the very top, it has an acceleration of negative 10 meters per second squared. And that goes to show that just because an object is stationary does not mean it has 0 acceleration, because acceleration is a change in an object's velocity. Now, as it accelerates back down on the ground, it's speeding up. It's getting faster and faster and faster and faster. A lot of people think that when something's speeding up, it has positive acceleration. That's not always the case. Yes, the object will get faster as it falls, but it's falling in a negative direction. So, it has a negative acceleration. And the acceleration is the same no matter where we look as the object's being thrown up or falling back down. All right, now for all types of motion, we can use these models to help us understand them. This first one comes from the definition of acceleration. You just got to do a little bit of algebra, but hopefully you can see how that's the same. This third one, I prefer to write it a little differently. This one is universal. It works for all forms of motion. Because let's think about constant velocity. At constant velocity, the acceleration equals 0. So this formula becomes this. And again, that should look very, very similar to our constant velocity equation. So this is our universal formula for motion. It works for every time that we have constant acceleration, whether it's constantly 0 or has a constant value like negative 10, that will always work. This middle one is a useful equation. It helps us study motion when we have no idea how long it's been moving. So that's another very useful model or equation. All right, projectile motion. We're not going to do a whole lot with projectile motion for the game this year. In the past we have, and in the future we may do projectile motion again if they have another throwing game, so I wanted to cover it a little bit. It's a study of objects as they fly through the air under just the influence of gravity. So to begin with, we need to understand that velocity is a vector. So it has a magnitude, like feet per second, but it also has a direction. And we represent it with an arrow. So all vectors are represented by arrows. So let's say we have something that's thrown. It's given some sort of initial velocity, and it's at some sort of angle. I can break this vector into two parts. One part is strictly the y part. The other part is strictly the x part. Now I can use a little bit of geometry, which SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So what this tells me here then is that sine of my angle equals opposite over hypotenuse. So opposite in this case is v naught y. Hypotenuse is v naught. I can stick this under 1, and I can cross multiply to find out that the v naught y equals v naught times sine of my angle. If I take a look at the cosine function, it's adjacent over hypotenuse. So here the adjacent is v naught x. The hypotenuse is v naught, and again I can stick this over 1 and cross multiply. And I can find out what the x component of this velocity is. So what this all means then is that we can isolate the velocity in just the x direction or the velocity in just the y direction independently. So again, just to reiterate this, we have SOHCAHTOA, but also we have the Pythagorean Theorem. So the hypotenuse squared equals a squared plus b squared. So we can take a look at this and we can find really anything we want to using just those two bits of knowledge. So in projectile motion, velocity along the x-axis is constant. So what that means is that the acceleration on the x-axis is 0. However, acceleration along the y-axis is not 0. It's a constant acceleration. And the acceleration on the y-axis is the same thing as g, which is our negative 10 meters per second, or 32 feet per second. Put negative there. So in your math classes, you may use 32 instead of 10, and that's okay. Now, it's not the goal of this class to really go into all of the theory. So what I provided for you are 3 equations that can help you. So the first one is how to calculate flight time. How long is this projectile in the air? The second one is to calculate the maximum height reached. And then the third one is for the horizontal range. I believe those are 3 things that are kind of important to know if you're in a competition and you're throwing something in that competition. So you can take a look at those. If you want to, we can do some problems in class just to solidify it. But it should be a lot of fun. We can do stuff like this if we need to. All right, that concludes video 1.